All right, let's get started. So, welcome to lecture 3. Today we're going to talk about user authentication, as you can surmise from the papers you guys read. So user authentication is a really key central problem in security. You see it show up all over the place, and it is often a source of some security problems as well. It seems like seemingly a simple problem to get right, like how do you figure out which user is accessing your computer system, but turns out to be pretty tricky to actually get correct and secure, and there's a bunch of technical issues that we can actually try to discuss in terms of what works well and what doesn't work well. And I think I want to sort of set as the context for this discussion is that user authentication is a fickle kind of a problem in a sense. There are certainly some technical issues that we can figure out and outright solve, but there's often a whole bunch of considerations in terms of what plan to put forward for any particular system design. And there isn't necessarily one right answer that every system should just use. And we'll see everything has some trade-offs. So really there's a lot of considerations to worry about in practice for how you should actually design your system to do user authentication. So just to remind you where user authentication fits in, we were talking about this sort of simplified guard model last lecture where we were imagining, or sort of logically, everything you want to expose to outside requests. We were talking about we want to put everything in a box for security, for isolation, and then if you ever want to allow requests from the outside, you have to have the requests authenticated first, and we have to figure out what principal is asking our system to perform some operation. So the guard's logical job is to first off authenticate who is calling and basically figure out what is this principal, so then we can do access control, log it, allow it, all this stuff. Make sense? All right. So what does it mean to build a user authentication system? So what has to go in the guard in order to make this happen? So at a fairly high level, there's really 3 parts that you have to worry about in designing some authentication system. The first thing is you have to be able to register for an account. So before a user can log in, you have to somehow add the user to the system. So add an account for the user so that the guard knows how to identify the user, how to authenticate them. And typically there's some kind of a secret involved. If you are talking about how are you going to authenticate a principal sending a request, most answers are of the form only the real user knows a certain secret, or only the real user has some device with a secret, etc. So some secret is being established typically during registration. Then, after you register for an account, there's the actual authentication step. So authenticate. So here, you're going to somehow check whether the request is really coming from the user you expect by checking a password, let's say, or other secrets, somehow figuring out who's calling. And the last but really important step, or part of an authentication system, is some plan for recovery. So we talked about the fact that when you register for an account, there's probably some secret that gets established to identify who is the real Alice or Bob in the system. But they might forget this secret. So it might be that whatever credentials that the user had might be lost, or maybe the device the user was using, like the security key that the paper was about, maybe that's lost. It's important for a real system to be able to deal with this. It would be not a particularly great system if you had to stop using the computer once you lost your security key. But most of the schemes sort of try to technically answer these questions, and you have to, at a system design level, figure out what makes sense for your recovery plan. So, as you probably saw in this U2F paper, they don't really talk about recovery, indeed, because it's not part of their scheme. You probably would design what makes sense for recovery for your overall system, but maybe use U2F for steps 1 and 2. Does that make sense? Roughly speaking? Questions so far? All right. Sounds good. So what's so hard about building this system? Well, there's a couple of challenges that might not seem entirely obvious at the outset. One challenge is that this picture that I drew over here of a user sending a request to a system almost never happens. It's not like I'm going to send an RPC message to some computer over Ethernet or Wi-Fi. It's almost always going to be the case that there's some other thing in this system that speaks on my behalf. So there's going to be some kind of an intermediate principle that is going to relay my request and might have to be trusted. So the picture you might have is I have a user on one side, and then on the other side I might actually have this guard that's waiting for a request to come in, but it might be the case that I'm actually talking to my laptop. And on my laptop, I type stuff in my laptop's keyboard. That thing is running a browser. That's the thing that takes my request. The browser might talk over a network, maybe to a load balancer, to some other web server. There's lots of moving pieces until my request gets to the guard. And in the worst case, all these pieces in the middle are part of our trusted computing base, so to say, meaning that they're all trusted to correctly relay what the user said. You can imagine lots of attacks if we don't take care to defend against this in some way. So, for instance, if you had malware running on your laptop, well, the malware could just monitor your keystrokes, or maybe doesn't monitor your keystrokes, just overrides them, waits for you to log in, and once you've logged into your bank, then it takes over the keyboard and types in, transfer $1,000 to the bad guy. So these are all sort of important things to keep in mind. The picture isn't sort of as simple as a user talking to a web server. There's really many more other components involved, and you have to worry about potentially what goes wrong if those components aren't trustworthy. Some of them you can avoid. We'll look at various cryptographic techniques in later lectures, how to avoid trusting the network, for example, maybe the server to some extent. But these are serious problems. For example, U2F, the paper that we read, actually doesn't really have a particularly great story for malware running on your laptop. They really worry about different kinds of attacks. But, despite the fact that they're susceptible to this, they realize it, still might be a useful system, but it's not going to be perfect against all kinds of threats. That make sense? Questions about this stuff? Feel free to submit anonymous questions to Kevin as well, if you like. All right. Question?
Why would it not be good at avoiding malware? Aren't they encrypting the
So your question is, okay, why isn't U2F good at avoiding malware? So we'll get into the details later, but one way to understand it, without even understanding any details of U2F, is what U2F does, it's help you log into Google or GitHub. You plug in your thing, you log into GitHub. At that point, you're logged in. The U2F story is over. You're logged in. At that point, the malware takes over and does whatever it wants on your GitHub account. U2F is no longer in the picture at all. You're already logged in. And there's sort of follow-ons to U2F. You could imagine maybe avoiding this problem. They're not particularly deployed yet, but it is a weakness, but nonetheless, it's maybe a useful system despite that. Makes sense. Other questions? All right. So another reason why authentication tends to be hard is that it's often not clear, in some sense, what the goal even is. So the notion of an identity is sort of the specification for an authentication system. The goal for us is to specify what principle is invoking this operation. But it's often hard to pin down what are these principles in reality. So we can talk about all these bugs in authentication systems, like, you can misauthenticate, you can break it, whatever. But what's the right answer you're expecting for any particular case? What I mean by this is you can sort of think of what's the ground truth? How would you, what principle should you be expecting for a request from any particular user? And just by sort of way of example, in the case of a bank, ultimately the person that's in charge of a bank account is probably identified by maybe a name and a date of birth. So at the end of the day, you walk into a bank and you give them some passport or maybe even a birth certificate as the root of trust for your identity there. And yeah, that's Nikolai born on this date. That is the owner of the account. That's how the bank thinks of you. It's not an email address necessarily. It's not a phone number. Those are sort of means to some end. But the root owner, the root identity for a bank is probably a name and a date of birth. Maybe more stuff. I don't know exactly what goes on in a bank system, but that's sort of the shape of an identity. That's fairly unique. Many systems you interact with don't actually think of you as the name on your birth certificate. And for example, for MIT, it's kind of a complicated system. I'm sure there's like many computers at MIT, but I think at some level, the account you guys have at MIT is sort of from admissions. It's an account for whoever submitted that application that MIT thought was worth admitting, and that's it. That's like who you are. They don't really maybe dig too deep into like, do you really have a birth certificate? At some level, what they care about is it's a student that we admitted. That's a ticket for one account. Other systems might actually have even weaker things like this than this, right? So many systems actually provide a much weaker guarantee where they don't really have ground truth, in a sense. They don't really know who you are, and the only authentication guarantee they try to provide is that step 2 matches step 1. What I mean by this is that whoever you registered, that's who we're going to authenticate. And the authentication system has no idea who you are necessarily. It's kind of a first come, first served style of identity. That make sense? So the degree to which you even have an idea of how you think of users affects how you might go about recovering accounts. If the only thing you know about an account is it's the account that was registered, well, you don't really have a whole lot of a basis to recover it if that authentication system is now busted. But in a bank, whatever authentication system I might have, at the end of the day, I could walk in and present maybe a passport or some other credential proving that's my identity. Make sense? So this turns out to be tricky. For many systems, actually, you don't really need a strong notion. So for example, for Amazon, probably it suffices to just track whoever wanted to buy goods. They don't really care what your name is or where you're from necessarily. Maybe all they care about is, well, you came, you shopped, they'll keep track of your shopping cart for you. That's the goal, and they don't really have a deeper notion of who you are. And maybe that's okay for some systems, but it's an important thing to keep in mind of what it is that you're actually trying to authenticate here. Questions? Yeah? So does this weaker model mean that when you log out, your identity is gone? Well, logging out is probably a separate thing. Like in all these guys, you can log out. I can log out on my bank website, but then I can log in. And the question is, how are they going to what does it mean for the right person to log in versus the wrong person to log in? And if you're sort of an omniscient observer looking at the system, is the right thing happening? Well, in a bank, you could say, it's like, that human, are they logging in? And you could say, that was right, that was wrong. On Amazon, it's not really clear, or at least from Amazon's point of view, they don't really have any idea of who you are other than, well, you registered, you authenticated, you logged out, you authenticated again. If it matches the registration, great. Otherwise, well, I don't know, maybe that's it. You need a new account. Sense? Other questions? All right. So let's talk about how you might actually implement various steps here. So let's maybe start with registration and see what are the various options you might have, at least in the system design level. So as we talked about in this weaker model, a pretty common way to think of registration is really a first come, first served basis. So this is something like maybe an email address at Gmail. So when you register for an email account with Gmail service, they don't really have a notion of who you are. You're going to establish a whole new identity. And your identity is going to be, well, whatever string that's not already in use. You can pick it. And at that point, that's just definitionally who you are. And you can go from there. So there isn't really any ground truth to this. You sort of establish a new identity in this registration process. Another sort of kind of a system design you might have is you might actually bootstrap your identity from elsewhere. So pretty common to use an email address as maybe your principal in some system that you're creating an account at. And this sort of both serves to figure out how to authenticate you for registration purposes. So I should be able to register the Nikolai at MIT.edu account on some website I've never heard of before because, they're going to send me a verification email, and that's who they're sort of reserving accounts for. They're trying to maintain this namespace of principals based on some other bootstrapping process. And sort of the last sort of thing that typically happens is some kind of an admin that creates accounts. So for registering accounts, some administrator, for MIT admissions, the admissions office goes to IS&T and says, we admitted these 1,000 principals. You can let them register for an account now, and we'll know who they are. Or for a company, when you get hired, the HR office, I guess, tells the IT organization, let them register for one account. So some kind of a process is important here to tie your authentication system identity to some broader notion in the system. Make sense, sort of? Some level may be simple enough, although gets mixed up in practice, but seems like a fairly simple, hopefully, thing to worry about. Question? You mean how the bootstrapping step? Say more about that? Yeah, so typically you might have a system like, I don't know, some website where even Amazon actually, sometimes you could go to Amazon and just say, I want to create an account to start buying stuff, and they don't actually require an identity. But you can also say, create an account for this email address. And they will check that you own that email address. They'll send you a verification email, and they'll use that as a way to bootstrap knowing who you are. So knowing that you had this email at least at some point in time is allowing you to have that principal name in Amazon's system. Now, probably the reason they do it is it helps them with recovery, because if you bootstrapped account creation from some system at one point, it might also be a good way to figure out how to reset your credentials if you claim you've forgotten your password or lost your security key, etc. So this registration step often correlates with how you're going to implement recovery in your system, because whatever led you to think, let's let that person register for an account here to begin with, is also probably how you think of reaching that person if you have no other way of getting in touch with them or no way to authenticate them. It's troubling for first come, first served, because there was no reason to believe this was, xyz@gmail.com. They didn't exist before. So for first come, first served in particular, it's not really clear how to do a principled recovery process, although so you have to really build up a recovery process yourself. You can't rely on other things to do recovery for you. Question from Kevin? Would SSL be another example of bootstrapping? Oh, SSO. Yeah, so SSO is a single sign-on. So systems like Touchstone at MIT, indeed, you can sort of think of maybe they all being one part of one domain, or maybe each server that uses Touchstone uses bootstrapping to get credentials from the Touchstone server, for example. Yeah, so similar idea there. Absolutely. Makes sense. All right. So as we were talking about, registration often goes hand in hand with recovery and trying to figure out what do you do if your user can't actually log in anymore. So maybe a negative example of how to do recovery that we saw in the first lecture is these security questions. that, if you go to a website and say, I don't remember my password, they might say, oh, what's your mother's maiden name, those kinds of questions. The thing to keep in mind is that these security questions are really an or policy, meaning that the person that can log in either has to know the password or be able to answer these security questions. Sort of the weakest side wins. What you almost might want is a policy that says, well, you have to know the password, but only if you forgot the password, then you can answer the security questions. But of course, you can't really enforce that. You don't know if the person forgot their password. You have to allow them the attempt for security questions. So that's why important to keep in mind. These or policies are really bad because the adversary gets the choice of whatever they feel like using to log in at that point. So how else might you reset credentials? Suppose you forgot your password on some website. Oh, you had some question? So your question is, how do security questions work in practice? Because they're relatively guessable. I mean, I think you have it, right? Like, they sort of work. You have to think at least a little bit. But I think it's not too difficult for a determined adversary to guess your security questions. I think one example that often comes up is, I think I didn't mention this one in the first lecture, there was this vice presidential candidate, Sarah Palin, that was popular, I don't know, almost a decade ago, and I guess was in the news recently as well. But she had a Yahoo email account, and her security questions were on her Wikipedia page. So someone broke into that by just going to Wikipedia. Now, he got in trouble. He got to go to jail. So it's like serious stuff. But technically, this is not a particularly strong defense. So, indeed. So how else might you do a better job of recovery? Yeah? Yeah, okay, so recovery emails, yeah, seems like a reasonable plan. Sort of goes with this bootstrapping plan, yeah, so it works pretty well. Yeah, absolutely, yeah. Yeah, okay, so you're saying that a small system like MIT, you might, I guess, go to ISNT and, call them up, or maybe at a slightly larger scale, you call up customer service and you say, I forgot my password, what do I do? Or like, my phone died, I got to reinstall Duo, etc. So the thing that's good about this is it will probably get you out of trouble. Almost any question, like, go to S&T, they'll be able to create a new account for you almost, if you ask nicely enough or you have a believable story. But the problem is that you have to really be careful that you have a concrete plan in place for what these people are going to do. Because if you just ask your users to go to ISNT, but you don't tell ISNT what to do, ISNT is going to be very likely to be subject to sort of social engineering attacks. Like, I want to reset your account. I'll go to ISNT and say, oh, yeah, man, I was running, I lost my phone, I'm this guy's email address, please reset it for me, that's who I am. I'm wearing a mask, you can't tell who I am. Yeah. So they really need to have a process in place. It's not just an answer to go to ISNT. It's an important question to figure out how is ISNT going to do anything at this point. So maybe they'll ask for or maybe what they should do, they probably do, is ask for maybe your driver license or MIT ID, check your face, ask for a passport, worst case. But they need to have some idea of how they're going to authenticate you now that they can't use the normal means of authentication. Other thoughts, comments? Yeah? Yeah, so maybe there should be sort of, many ways to log in. So then if you lose one way to log in, you can still do something else. So for instance, with Google, you can register like your two-factor app on your phone and a security key and a phone number. So it basically prevents the user from having to go into this recovery process to begin with by making the authentication more robust to begin with to various sort of failures or mistakes. Yeah. Yeah. Okay, so you're basically saying, okay, sometimes the answer is no. So I think that's actually a very legitimate thing to say, is that in some cases, the answer is you can't recover, and sort of maybe the next step of what to do is just create a new account. it's too bad. I mean, you can still use the system, but just you're going to have a new GitHub username. And might be not an unreasonable story here, because maybe you don't have any basis to believe who it is that's trying to recover. And what's going to happen, for example, in GitHub, it's going to be up to you to convince whoever you're collaborating with that, oh yeah, it's me on the new account. And maybe those collaborators actually have a much better idea of who you are as opposed to GitHub. Like the people that you're collaborating with on some project might be able to tell that, oh yeah, it's the same guy. Let's add him to this GitHub ACL, whereas GitHub doesn't really have a deep understanding of who you are. So maybe the level of GitHub usernames isn't really the level at which you can securely reset things. That's a good point. Sometimes you just shouldn't recover. Make sense? Any other thoughts or ways to reset? I think this more or less covers it. So, there's some generalizations, of course, of emails, etc. Send a SMS text, whatever. But roughly speaking, I think this is a pretty good perspective on how you might architect your recovery in your authentication system. It's tricky to get right, though. Like, you really have to think hard, especially with this escape hatch of calling customer service. I think many real-world attacks actually work this way because companies might not have a fully thought-out plan, or maybe they try to think hard, but it's like there's not a great answer if you don't actually have an idea of what the root of correctness is for an identity. Make sense? Questions? All right. So let's talk about, I guess we talked about sort of all the periphery, registration, recovery, all the stuff. Let's dive into actual authentication schemes and look at the details. So the first one that's worth understanding as a baseline, of course, is passwords. And you guys did read this somewhat inflammatory blog post from Microsoft. I mean, there's like slightly over the top, basically saying nothing matters. I'm sure you can quibble with a bunch of technicalities, but I think an important point of their blog post that is worth maybe listening to is that in terms of achieving security from a password-based authentication system, the things that matter are probably not the exact password that a user chooses, but I think in practice the importance is much stronger on other aspects, like how do you deal with various forms of attack, like brute force attempts to log in, preventing the password database from being stolen, authenticating user with other factors, perhaps, etc. So passwords, there's of course some difference in terms of security of the password you choose, but in the grand scheme of things, these guys look at it from a very data-oriented perspective. They're not thinking, oh yeah, this like super motivated user is going to go and choose a fantastic password and that'll be great. They're looking at sort of the distribution of all the users Microsoft has, and by and large, the top 10% of the users versus the bottom 10% of the users, they might have different kinds of passwords, but not different enough to matter for serious security attacks working or not working. I think that's roughly the point they're trying to make. So to understand sort of passwords, I wanted to maybe show one important slide. So this is a kind of an interesting data set. These are the top passwords from a leaked list of 32 million passwords. And what this is showing is, for example, that out of these 32 million accounts in a database that was leaked quite a while ago at this point, but the stats surprisingly look pretty similar. Out of 32 million accounts, 290,000 of them had the password 123456. So users choose an exceedingly small set of passwords, and lots of popular passwords account for many accounts. And a little bit surprising that such popular passwords like uppercase password is 60,000 accounts out of 32 million. These are really popular passwords. And the thing to keep in mind as a result is that the fact that these passwords are so common means that you really have to worry a lot about guessing attacks. So, as a simple example, right, if I were to just guess 1, 2, 3, 4, 5, 6 for a random account, I'd be right some non-trivial fraction of the time. I think it's almost 1% in this case. So that's shocking. Like, I should try 100 accounts. With that password, I'll log into one of them. So it's really important to prevent these kinds of guessing attacks. And the sort of, maybe the more statistically sound statement is here in the bullet point that, not only is that password account, like 1, 2, 3, 4, 5, 6, accounting for 1% of accounts, but if you take the most popular 5,000 passwords, it covers 20% of accounts. Sort of a crazy number. It's like a very fat head distribution in some sense. Like the popular passwords account for a large, large number of accounts. So it's important to prevent guessing of all kinds. So it would be bad if I was able to make 5,000 guesses against one account, because then I'd be right 20% of the time. But it's also disastrous if I can make one guess even for every single account in the system. So it's important to throttle guessing, not just for a given account, but also across the board. It's not a good idea to allow one guess for every account either. Tricky stuff to get right. So this is, I think, the kind of defense that the Microsoft blog post is arguing for, that you have to worry about preventing these kinds of guessing attacks across accounts, for instance. Questions through Kevin? Yeah, so password managers, we'll talk about them in a second. I think you have a trait of what the pros and cons are. I think you get much stronger passwords, so you avoid falling into this trap. So effectively what you have from a password manager isn't really a password anymore that the user knows, but really some sort of a random key that your password manager and some server knows about. But of course, one downside of that is that this password manager now has all your passwords. And there is a distinction, because with this password, even though it's kind of weak, at least your computer doesn't have it stored on the computer itself. So if someone breaks into your computer, there's a difference between compromising your computer and compromising your head. Like there's some password in your head, maybe it's not super strong, but it's there, it's not on your computer. So you can talk about your computer being compromised, but maybe your password is still secure until you type it in, or who knows what. But with a password manager, there's not really anymore a difference between the human and the computer. So if someone compromises your computer, they probably can just grab all your passwords. That's it. That's your whole identity. If there were 2FA involved, maybe that's a different story. But I think it's important to think about authenticating the person in some way, even though it might be hard to convince a person to store lots of bits in their head in a password. It is important to have some kind of an authentication credential there. And as an example, we talk a lot about passwords, and I think to us, passwords seem like of course it's a bad thing, but actually phones have these PIN codes all the time. So when you unlock a phone, you're using a thing that looks a lot like a password, and those actually do work pretty well. And I think the difference, when you get down to it, is that with a password, we typically talk about authenticating over a network. And there, it's much more difficult to rate limit, because requests come in from anywhere on the internet. You don't know where the user is. It's harder to prevent guessing attacks. There's many users involved. Whereas on a phone, there's really sort of a single device that's much more capable of implementing much more aggressive rate limiting. So on a phone, you could easily rate limit to 1 guess per minute, for example, and a max of 10 guesses or something very aggressive like this. That would be unreasonable to do on the internet, because a bad guy would just lock you out of your own account. But on a phone, you know when you're making attempts. So these passwords are still a good idea in some cases, in some shape, but it's important to understand how to use passwords securely, in a sense. Hopefully it makes some sense about password managers, etc. I guess we'll talk about password managers in a second. Other questions? All right, so that's one conclusion about passwords. You really have to worry about guessing and limiting attempts. The other thing that also I think the Microsoft blog post makes some deal about is worrying about the format of passwords versus the entropy. So the thing that you want for a password is that it's difficult for a bad guy to guess it. And there are some passwords here that have numbers. Some of them have letters and numbers, like ABC123. Just because it has letters and numbers doesn't make it a good password, right? Like that's the 10th most popular password. And the thing to realize is that the bad guys understand this distribution of passwords very well. The bad guy is looking at this table just very much the same way that we are looking at it. So if a bad guy has a question, what's the most likely password and what's the next most likely password, they'll go down this list, even though the fourth password has both uppercase and lowercase characters. So the thing that matters for a password is the probability of some user picking that password, the entropy of that whole password, as opposed to the characters out of which it's composed. So, important to keep that in mind when setting sort of the policies for your passwords. Many systems try to enforce some kind of format requirements, but it doesn't always work out very well. Like if you ask a user to add a number, they'll just add the number 1 to the end, and it'll satisfy the requirements, but the bad guys know this, so they'll just try adding a number 1 to every end of a password as well. Make sense? So entropy matters a lot for passwords, or pins, or whatever it is that you want to worry about. And maybe the last thing that's important to realize about passwords themselves is that users often share them across systems. So the point here on the slide is that there was another dump of passwords from a break-in to a different computer system, and the distribution was the same. So users pick the same passwords over and over on all computer systems, and from some other more careful analyses of these data sets, turns out the same user often picks the same password on 2 systems, just because it's easier to remember. It's fairly natural, but important to realize that this is how users are going to use passwords and design accordingly for that. Make sense? Questions? All right, so one fairly obvious question that, oh, yeah, sorry. Good question. So the question was, are things like fingerprint readers or facial recognitions better than passwords? Fantastic question, actually. So what do you guys think? So what's the, like, should I use a fingerprint or a password? Yeah. Okay, so you have a point about privacy. So a fingerprint probably reveals something about me, where my password maybe doesn't. Maybe I'll come up with a random password. Anyone could have come up with that. Okay, so there's something there, yeah. Other thoughts? Yeah?
I think currently the law says that they can force you to use it,
Okay, so you're saying some laws basically says you can't use a fingerprint. Okay, so that would be an unfortunate thing, but indeed, the regulations are funny. But imagine that you're allowed to fingerprint someone, yeah. So someone had a comment back there? Okay, so proposal is to avoid the privacy problem with fingerprints, let's hash the fingerprint. Fantastic. So maybe we'll even have some kind of a hash that is like error correcting, like regardless of how I scan my fingerprint, I'll get the same hash. So that'll be cool. Yeah, maybe. Comment? Okay, so you have a point that, like, yeah, okay, if I don't have a finger or like something happens to my fingerprint, I can still log in. Maybe a less drastic version of this story is actually that you only have one fingerprint, or maybe like a small number. I don't know how they evolve over time, or if you can get a new one. But it's very expensive to get a new one, I imagine, even if it's possible. So the point is that things like biometrics are really best thought of as an identity as opposed to an authentication system. So your sort of face or your fingerprint is probably more related to almost your identity or something along these lines, or sort of in-person authentication at the very least, and not authentication over the network. The problem is that if you're talking about a situation where I have my client machine and I'm talking to a server over the network, then I can send my fingerprint image or a picture of my face or whatever it is to the server. But the bad guy, that's the way to think of it. What does the bad guy have to do to log in as me? If the fingerprint is my password effectively, then the bad guy just has to send my fingerprint or face to the server as well. And it's pretty easy to get my face probably. It's like I take a picture of me and you can log in as me then. Or for a fingerprint, if you compromise my account on one system, now you get my fingerprint, you can log in everywhere, by definition as me. Or if I leave my fingerprint, on this chalkboard, you can log in as me now. So that would be really unfortunate. It's really best thought of as an identity. Now, where biometrics work better is where we're talking about logging in sort of physically to some device. So we know that the user is in front of the device right now. Technically, the way to think of it is that the device has sort of a secure I/O path to the fingerprint reader or the camera, so that the device knows, I'm reading the data of the person in front of me right now. And at that point, that's a different story. Now we're actually sort of looking at the face of the person in front of the device, like in an ATM or a smartphone doing facial unlock. iPhones do this. I think Android devices do it as well. And there, you can actually do this in a more sensible way. Because for a bad guy to try the same attack, they'd have to first steal your device, much more complicated than just sending your picture over the network. And second, the device usually implements some fancy schemes to ascertain that it's not just looking at a picture of a face, but actually it's looking at a 3D thing in front of it. So we'll look more at this in a case study paper in a couple of weeks of how Apple's iOS devices do this. But roughly speaking, in iPhones, there's some kind of an infrared dot projector that actually projects random dots on your face from the phone. And then when the camera looks at you, it expects to see those random dots. Otherwise, it just concludes that it's looking at a photograph. So you can actually do some physical things as a device to authenticate biometrics that you cannot do over the network. So biometrics work okay for authenticating to a physical device. And over the network, they're really more of an identity scheme. Kevin?
Can you make the fingerprint reader sign a challenge to the server?
Yeah, so can you get a fingerprint reader to sign something from the server? So I think you can, of course, reduce it basically to the device case. So if your device is some kind of a trusted fingerprint reader, then yeah, you can basically turn this system design into, think of it this way, the user authenticates to this trusted fingerprint reader in front of them, and if the server trusts that this fingerprint reader is good, for whatever reason, then, yeah, we can sort of talk behind the scenes to the server, and the server can say, oh yeah, I trust this guy. Did you actually see a real fingerprint? So this could work. And sometimes I think iOS tries to get something like this where they have an enclave chip in the phone which effectively encapsulates this trusted fingerprint authentication scheme and might be able to provide some message to the server saying, yep, iPhone serial number 123 authenticated a fingerprint. You had a question? Okay, so your point is like, on the back of my phone, if I was using fingerprints, well, in the front, there's also fingerprints. So I think there's sort of twofold answer. One is, yes, at the end of the day, yeah, there's like, the information in your fingerprint is in lots of places, but the fingerprint readers, at least good hardware fingerprint readers, require some sort of a physical check that this is a live finger, and it requires slightly more cost for the adversary to actually fabricate a silicone finger that's warm, that has pulsation from a pulse, that looks real. So it's not a perfect defense, but it's pretty good, right? Like if I was leaving my phone here, I'd probably be okay walking out here for 10 minutes, and probably you guys wouldn't be able to fabricate a silicone finger of mine in 10 minutes. So yeah, it's good for many things. Other questions? How do you rate limit guesses without also having the unfortunate side effect of DOSing the account? That's tough, and I think this is what the Microsoft paper is talking about. That's the hard problem to solve for passwords, as opposed to getting slightly better password quality. I think what you have to do is really try to understand where the request is coming from, and maybe rate limit per IP or per IP range. But it's tricky, indeed. I think a determined attacker could probably trigger the rate limit on your account in various ways that you'll have a hard time getting into. Now, one way this could be avoided is if you have a stronger credential to present. What I mean is that if I'm already logged into my Gmail account on my laptop right now, you guys could try to log into my account, and you could probably trigger the retry limit on my password authentications. But my browser already has a cookie saying that's me. So I'll be able to still use my existing devices. Establishing new sessions might be tricky, of course. Yeah. All right. Other questions? All right. Interesting aside on biometrics. Useful thing to think about. All right. So one thing worth understanding with passwords, I guess we talked a bit about password managers. Handling passwords securely is tricky. The naive thing you might want to do if you want to store passwords on a server is to just store a table. So you might have a table like user and password. So we'll have Alice with some XZ54 password, Bob, I don't know, maybe 1, 2, 3, 4, 5, 6, whatever. We have a table like this. Pretty straightforward to imagine the code for authenticating this stuff, right? So you just, user comes in, sends a password to the guard. The guard just looks in the table and says, is that the right password? The problem with this, sort of given all the sort of weaknesses of password we talked about, is that it's really easy for an attacker that breaks into one system to now take the passwords of all the users and try them against a different system. So that's really undesirable because users do share passwords, and that's one of the actual attacks that the Microsoft paper talks about, blog post, being a real threat. So one thing people do to try to avoid these kinds of password disclosure attacks, so I should say, like, this way of storing passwords is exactly what gives us these data sets that you see on the slide, that people do the sort of straightforward thing. They get compromised. Very interesting for understanding passwords, but not a good way to store them. The better way to store them is to use hashing. So the idea here is that instead of storing the raw password, what we should store is the username and a hash of the password. So we'll have something like Alice, a hash of Alice's password, Bob, a hash of Bob's password. This is a pretty nice way to store it for the following reason. You could still authenticate. The pseudocode for authenticating, you can imagine, is fairly straightforward. Instead of checking that the password supplied to you matches the table, you take the password supplied by the user over the network, you hash it, and you see if the hash of the submitted password matches the hash that you stored in your database. Still lets you authenticate users, but now disclosing the stable, if someone breaks into your server, doesn't immediately give up the passwords of the users. So that's a nice property. Pretty much every password storage system does something along these lines. Questions? How this works? Hopefully this makes sense. There's two sort of more degrees of sophistication that real password storage systems worry about. One is they worry about pre-computation attacks. So what I mean by this is the following. So a hash is difficult to invert, right? So the way to invert a hash is pretty much the only way you can do it is try lots of things. Maybe you'll try it according to the password distribution, of course. You wouldn't start with all zeros and go to all ones. But still, you have to do lots of brute force attacks. And the problem is that you can do those brute force attacks once ahead of time, spend a lot of time computing all the hashes of all the passwords. So you might generate some kind of a table that says, here's all the passwords I think you might possibly have, and I'll compute the hash of every plausible password. And then, when I compromise a server, I'll just look up all the hashes I see here in this pre-computed table. And the bad guy might even sort of band together into a group, spend lots of money on EC2, pre-compute a giant table, and then they'll be able to use it to break everyone's passwords very quickly. So, to defeat these pre-computation attacks, what many systems do is what's called salting. So instead of just hashing the password, we're going to add an extra field to this password table called a salt. And a salt is really just a random number. You pick a random number every time the user registers or changes their password. Whenever their entries change, you pick a new salt. And where the salt is used is that what you store is a hash of the salt concatenated with the password. So here we might have Alice, and there's some kind of a salt, 54891, and some hash of her password with this salt. And we have Bob with a different salt, 10322, whatever. And the important thing about salts is that there's a lot of entropy in the salt because the computer is picking these. These could be random 64-bit numbers for all we care. And as a result, it is extremely costly now to pre-compute the table of all possible salt and password combinations. Because even though there might be only 5,000 really popular passwords, as we saw on the previous slide, there's 5,000 times 2 to the 64 possible ways this could turn into a hash input. So you'd have to pre-compute 2 to the 64 times 5,000 hashes in order to invert this table now. This would be a very expensive pre-computation task. Now, I guess I should say, you can still authenticate, right? So by adding the salt, pretty easy to check that the user can still log in. So if a user tries to log in with a password, you look up their salt from this table, and you hash the salt from the table with the password the user supplied. And if they match, then, it's the right password. If they don't match, something went wrong, not the right password. Question, Kevin? Is it better to hash on the client or on the server? So if you hash on the client, it might have some properties about hiding your real password, but it doesn't actually prevent your password from now being directly visible to the server. Because if you hash on the client side, what I mean by that strawman proposal is when I try to log into a website, I take my password, I hash it, and then I send the hash to the server. Well, at this point, the real password is effectively the hash of my password. The pre-image, the password I typed in doesn't matter because I would send the same hash to server 1 and server 2 and server 3. So if someone compromises my account on server 1, they take that hash and send it directly to server 2. They don't have to compute the hash because over the network, only the hash shows up. So hashing on the client might be good for something, but it doesn't really help for this problem. Another question?
Is there an advantage having one salt per user versus one salt per password table?
I think the advantage is just, well, having a salt per user is just super easy and super easy to think about. So I think there's sort of, I don't think you'd win anything serious by having the same salt for all the users. It might be problematic in some corner cases, like you'd be able to tell that two users have the same password, whereas with different salts you wouldn't be able to tell this. I don't know, minor differences. Practical systems just store a different salt. Yeah? That's using two different salts. Well, I mean, bigger salts are better. Two of them, I feel like, is just the same length. So, probably you want a salt that's like 64 bits or so, then you're probably good to go. You don't need it to be that much bigger. Whether you think of it as 64 different bits or one 64-bit thing, doesn't matter, effectively. Yeah. Other question back there, yeah? Okay, so the question is, so we're storing the salt right here. So if this database gets leaked to the bad guy could try to brute force these hashes. So absolutely, you're right. The database has all the information needed to check if a user's password is correct. And by definition, you could brute force that. I think the point of the salt is that it prevents the pre-computation of this kind of a table. So, if you want to get this, okay, so this is your point is that if your goal is one account, then the salt thing is really all about, the salts really prevent against sort of cheap attacks against lots of users. For targeted attacks, salts, I guess, do kind of prevent this pre-computation somewhat, but at the end of the day, then it's just a question of, are you pre-computing it ahead of time, or doing the same amount of computation targeting a user once you get their salt? And they're, I think, not as big of a deal. You're right. So makes sense. And the last thing that matters in practice is this hash function should really be something expensive. So typically hash functions on this slide, it's SHA-256. That's, I guess, correct, but not very secure because it's super cheap to compute. You want something that's as collision resistant or as cryptographically secure as SHA-256, but it should be expensive to compute. SHA-256 can do sort of hundreds of megabytes per second on a modern computer, maybe even gigabytes per second. That's a bad thing because it means the computer can brute force lots of passwords per second. But you want some H there's hash functions called PBKDF, 2, or scrypt, or bcrypt. So these are basically hash functions that are super slow. They could take like a second to compute one hash on a CPU. And for logging in, that's not really a huge deal if it takes a second to log in, but it is a big deal for limiting brute force attacks because the bad guy also will take 1 second for every guess at your password. Now still, they can probably do it for at least the popular passwords that we saw on the previous slide, but for maybe strong passwords, maybe this is providing some degree of security. Make sense? Question? They're kind of, at the level that we can describe here, you can think of them as iterating SHA-256 a million times. There's something a little bit more clever going on there. But the mental model, I think, is about right. Yeah. Other questions? All right. So that's the plan for, I guess, storage of passwords. If you have to use passwords, this seems like the way to do it. There's some other actually clever things people have come up with. There's a challenge exercise on the next lab, lab 2, where you could implement a fancy version of salting where you actually store the salt in a separate table. You know, there are some clever tricks you could do, but this is like the main dimensions to think about in terms of password storage. All right, so now let's talk about two-factor authentication and how to really augment passwords. There's only so much juice you can get out of a password, really. So how do we actually do better? So augmenting passwords. So some kind of a two-factor authentication scheme. And the first thing that I want to describe is a fairly simple scheme, SMS-based two-factor authentication. You guys have probably all interacted with a system like this somehow. So let's talk about, I guess, yeah, SMS-based, the first version. So the parties we're going to have here are still, we're going to have some kind of a client computer that the user wants to log in on. And here we have our user. And the computer is going to be trying to log into a server. And the server probably is going to have, a table of username. They'll probably store a password, a salt, all this, hash stuff that we just talked about. But we'll focus on the two-factor thing. So in order to authenticate users with the second factor of SMS messages, we're going to need to store their phone number that we're going to send the code to. So what's going to happen is that when a user tries to log in, they're going to send their username and a password to the server. And now the server is going to generate a new code, random code that no one knows at this point, and it's going to send it to your phone number. But also we're going to have to store it so that we can later check if you got the right code. So the server probably needs to store the code here in the table. So we might have Alice, and here is her phone number, something, and when Alice tries to log in, the server is going to generate a random new code here, 5, 1, 2, 3, 4, 5. That's the code. Now the reasoning is the server just generated this code. It was random. No one knows it unless they guess big numbers. So that shouldn't happen. And now what the server is going to do is send this code to an SMS. So it's going to send this code 5123455 to the user's phone number. And now the cell phone network is going to get in the middle, take your SMS message, somehow route it all the way to the phone of the user, and out pops this code on the user's screen, ideally, which the user is going to re-enter into the computer system, or whatever, 512. Make sense? Question? So okay, your question is, doesn't this create the same problem as leaking the table for the passwords? So the seeds are a different scheme. They're not the SMS-based scheme. We'll talk about the TOTP scheme later. But here, you're sort of right, this code is sensitive. If you leak the table, you can now authenticate as the user. You can imagine that it's pretty easy to maybe add an expiration date to say, I send this code now, or this time, T, and only accept this code if it's within 5 minutes of the time you sent it or generated it. So yeah, good point, yeah, absolutely. Other questions about this scheme? Fairly basic, yeah? So why is it secure? That's a good question. How many digits should we have for security? Or how should we think of when is enough? How many digits are enough? So the nice thing about this is probably relatively easy to rate limit. So when a user tries to log into a server and provide a code, we can do a check, and we know that the check succeeds with probability, I guess, 1 out of a million if it's a 6-digit code. It's a fairly small chance that an adversary guesses this right by chance. And we are going to rate limit it, very much like passwords. So I think this has the same sort of feeling as password retry attempts. About the same entropy as a password, I suppose. So it like doubles the strength of a password. Yeah. It is slightly problematic, but I guess the way to think of it is that maybe this is not as big of a deal because you also have to know the user's password and I don't know. But you're right to think about like what's the probability of an attacker succeeding. If an attacker can guess the two-factor code for all users across the board, well, if they just need to guess against 1 million accounts, they'd be right for one. You know, might be a problem, so maybe you need to worry about that as well. Yeah. Make sense? All right. So this is roughly the scheme, how it works. The user sort of manually types it in, and the computer now sends the code to the server, and the server compares it. So what's good about this scheme? Or what's bad? Any thoughts? All right, so one nice thing about this is that it's actually pretty easy to deploy. So if you are trying to add two-factor authentication to your system, probably pretty easy to set up. The user doesn't need a new computer. They already have a phone. You can ask them for a phone number, relatively low overhead. So pretty easy to add to incrementally to a new system, to an existing system, I mean. Got a question or a point? Sorry? Yeah, SMS spoofing. Okay, so I guess, yeah, so one way to maybe talk about the class of problems you're mentioning is that there's this big thing in the middle here, like this cell network. It's probably much bigger than anything else in this picture. There's like tons of computers, tons of customer service agents that are willing to change people's phone numbers. There's a lot of ways to attack this thing. So if this serves as a big part of your security plan, it's largely outside of your control, which is problematic. So the kinds of attacks maybe we're thinking about here is that if someone wants to hijack the two-factor authentication code for my account, maybe what they do is call up T-Mobile and say, hey, I'm Nikolai, like I lost my phone, here's like an invoice for my, I don't know, show my MIT ID, and it's like, okay, well, reset my phone number. This stuff happens, right? Like it's actually not too hard to walk into a T-Mobile store, call them up on the phone, and ask them to like, please give me a new SIM card. If you claim you've lost your SIM card, they're not going to have much of a way to authenticate you. They might try to ask you for a driver's license or something, but maybe not. Not all these customer service agents might be very diligent. So I think this is potentially a big weakness in these SMS-based schemes is that they rely on this very large component that doesn't have very precise behavior. There's many ways in which you might get someone's SMS messages. Make sense? Yeah? Yeah, so that's another sort of family of attacks, the social engineering attacks of a different kind, where maybe you have indeed a two-factor code set up with some service. Like maybe this is MIT's Duo two-factor SMS, two-factor codes being sent to your SMS phone. Someone calls you up and says, oh, I'm from ISMT. Your email is running out of quota. You must give me your code now, otherwise the president will, I don't know, not get something. You might get a code right then and there in your phone because the bad guy just tried to log into your account and a code got sent to your phone. And if you now tell this code to the person on the phone, okay, well, you've given away your code, right? So exactly right. I think these kinds of phishing attacks are a real problem in these two-factor schemes that this U2F paper is really trying to address. That make sense? Questions about these phishing attacks? Yeah. Why are they digits and not letters? I don't know. I think historical reasons and also some, no particular deep reason. I think all kinds of historical artifacts of how they are usually derived. Nothing terribly exciting, I think, yeah. So just to clarify, I guess, so these phishing attacks are a big problem with SMS because there's no real way in which the user can tell if they're supplying the code to the right server because they're just typing it into their computer. They don't really have a good sense of where the computer is going to send it to, or if it's on the phone, they don't know who is on the phone talking to them. Make sense? So a related family of schemes, actually maybe, one thing I wanted to finish up is maybe the discussion of weaknesses or strengths for this SMS-based scheme. So certainly one strength is deployment, and one actually, maybe plus or minus, is recovery. So one cool thing about SMS codes is that you made recovery someone else's problem. Recovery is now the problem of the cell phone operator. So if the user calls you up and says, my two-factor codes won't work, I lost my phone, you tell them, well, yeah, good for you, or whatever, go to T-Mobile, they'll figure it out, then come back to us, then it'll just work. So you sort of outsourced recovery to someone else. That's a very, I guess, maybe a big reason to use it. The problems, as we talked about, right, is really trust on the cell phone network and also phishing. That's potentially a big problem, especially for high-value users. Probably it's not going to be mass phishing across all users at Gmail, but if someone wants your account, they might target you and might succeed. So a different scheme that you might also have used is called time-based one-time passwords, or TOTP. And the way this scheme works is that instead of having the server send a code to you, the server maintains some kind of a secret for a user, often called a seed, some sort of seed S. And what's going on is that the codes, instead of being sent to you from the server, they're sort of deterministically computed. So the code is the hash of the secret and the current time. So this is why the codes keep changing all the time in your authenticator app. The authenticator app on your phone, as a client, you have a phone here, or whatever, some kind of a extra device, and it's got the same seed S, and it keeps hashing that seed S with the current time, and keeps changing it as the time advances. So that's the 6-digit code you're seeing in your authenticator app on your phone, is the hash of this shared seed with the current time as the time keeps jumping every 30 seconds. And the server has the same thing going on. And there, you just enter the same code into your computer. That gets sent to the server. The advantage is that at least now the cell phone network is out of the picture. There's no cell phone network. As long as you share the same secret between the server and your phone, you're good. But, of course, now you're back to having to solve recovery yourself if the user loses their phone or damages it, etc. Make sense? In terms of phishability, though, all the same things apply, because you could trick the user into entering the code on the wrong website. Make sense? Question? Yeah, so right, you can just like send this seed over the wireless network and everyone can listen. Probably you'll send it over a TLS encrypted channel maybe, or something like this to initiate, at registration time, you somehow distribute the seed securely in a way that hopefully the attacker can't intercept. Question? Oh yeah, here the seed is really sensitive, right? So one nice thing about the phone-based, the SMS thing, is that there's no real secret, right? Like the secret is really short-lived, this code, whatever. After 5 minutes, it doesn't matter. Here, the seed really matters. So this is like the password. Except you can't really hash it, because if you hash it, it's useless. You can't do this TOTP thing with it. So indeed, right, like so you can do all that nice hashing stuff to the password database, but this seed just has to be like this on the server somewhere. Maybe you'll carefully box it away into a separate server that only deals with seeds and maybe is less likely to be compromised, but it's got to be there somewhere in plain text. Yeah, absolutely. Good point. Other questions? Comments? All right, question there. Yeah, they're basically a hash of like a special format instead of a time. I think it's like, effectively, 0, 1, 2, 3. You like hash something other than time. And the server now needs to store, in addition to the seed, it also needs to store the used values, basically, so that you can only use them once. Yeah, but that's roughly what's going on, is that you can either hash the time, or you can hash a special recovery integer value, and you'll set an extra bit so they can be confused with the time. Now, yeah, absolutely. Good question? why would you use TOTP versus SMS depending on the seed compromise? I think one big deal is that you don't trust the cell phone network. So that's one nice thing. I think, if I was having to design the system, the likelihood that someone's going to break the cell phone network is probably higher than my server getting broken into, maybe. Maybe I'm overestimating how hard it is to build a server. I don't know, but we'll see. Yeah. Let me describe U2F, and then I'll come back for more questions. Let's quickly sort of start discussing U2F, and then we'll sort of compare them and see what other questions you guys have. But I wanted to start describing U2F by first describing a strawman plan that is sort of a simplified U2F, and then we'll add various aspects of U2F to it to see what they're good for. So the base plan for U2F is that you have your computer, and effectively, I guess your browser on your computer. And this browser is very actively involved in authenticating you, sort of more so than in TOTP or SMS schemes. And the way this works is that you have your device, the security key, and in the simplified version, what's going on is the device has a public key, kpub, and a private key, kprivate. And when you register your device with the server, you send kpub, the public key, all the way to the server. And this is what's going to allow the server to authenticate you. And just as a reminder of the things we're going to use here, we're going to use cryptographic signatures. So they're basically a scheme where you can call sign with a private key, so kpriv, on some message, and you'll get a signature out. And then you can verify the signature if you have the corresponding public key. So with kpub, you can verify a message with a signature, and that will tell you whether the signature is good or not, okay or not. So the way U2F works in the simplified model is that the server generates some kind of a random number, kind of like the random code we had for SMS, except that here it's, I think, longer than 6 digits. And typically in the cryptography, it's called a nonce, for a number used once. And this challenge is sent to the browser to authenticate the user. And in the simplified world, the browser just relays the challenge to the device, and the device signs it. So the device signs this challenge with its private key. And this is the signature, and this signature gets sent over to the server. And the server just calls verify to check that this signature is a correct signature of the challenge the server asked for with the public key registered for this user. I guess I should say, table user key, Alice has this particular key. So the reason this works out now, the reason the server might trust that the real user is trying to log in is because this is a new value the server picked, the nonce. Should have never existed before in the world. New 64-bit number, or 128-bit, never before in existence. Never should have been signed by anyone for that matter. So the fact that now you get a signature back that verifies with the corresponding public key means that the user's device must have seen this thing and signed it, and now sends it back to you. So that's the reasoning process by which you might decide that, this signature S should convince the server that the real user is trying to log in using their security key device. Make sense? So that's the way sort of a simplified version of this protocol works. Question? So in the real thing, they can generate these on the fly, and they have a clever trick for not having to store them. They offload the storage onto the server. But we can think about a simplified world where there's just one key for now, and this also works out, or sort of gets at some of the essence of it. Yeah. Question? So they don't really do GPG in the sense that, so they call this verify function on the server, which is the same thing that GPG-verify would have done. So they verify that the signature is a valid signature on the message that they chose under this key that should have been corresponding to the user's security key. So they do check that it's the right nonce signed by the right key in this signature. So let's quickly talk about one sort of problem or one thing that I guess this does solve is you can't reuse the signature multiple times, so that's cool. Because if you try to log in a second time, if that hacker grabs your signature, they can't use it a second time to log in as you, because the next time the server would have picked a different challenge. So the signature is no longer a signature on the most recent challenge. So that works out well. The thing that doesn't work out well is that this is still susceptible to phishing attacks effectively, meaning that the same signature is potentially going to work for many different sites. So let me sketch out this phishing attack so that we understand what needs to be solved in this strawman U2F protocol. So the phishing attack that I'm talking about is that you might be, as a browser, maybe the bad guy tricked you into going to a website that the adversary controls, like bank.com, mistyped version of the bank. So your browser goes to this site and tries to log in with U2F. The first step is the site gives you a challenge. Well, the bad site isn't going to generate its own challenge. It's going to talk to the real bank behind the scenes, as if it was its own browser. And the real bank is going to send it a challenge because it thinks, oh, someone's trying to log in. Now, this fake bank takes that challenge and sends it back to you. Here's the challenge. Now, if your device gets this challenge and just outright signs it, the way we showed here, the signature you're providing to the fake bank.com is the same signature you should have provided to the real bank. What this means is that when you log into the fake bank by providing this signature, the same signature can be used by the attacker to immediately go back and log into the real bank. Does this make sense? So there's nothing about the signature that ties you to the real bank yet. So this is basically where the clever thing of U2F really comes in. And the answer to what they do is the browser tells the device what website you're trying to log into. And the reason this works well is because as a human, you might be really not paying attention. You might think this is close enough or looks good or whatever. But the browser really knows this is the URL you're at. So what's going on in the real U2F protocol, one sophistication among many, is that the browser actually sends the challenge and the origin of the website you're visiting to the device. So the origin is basically the string HTTPS, mail.google.com or something like this. Or I guess maybe in this case it's like HTTPS bank.com. That's the origin that you're trying to authenticate to. And then what happens is the device actually signs not just the challenge that the server provided, but also what it thinks is the server that it's sending the response to. So the signature that comes back from the device is signing with the private key both the nonce, or the challenge, and the origin name. And now the cool thing is that when the server gets the signature, the server needs to check both whether the signature is a valid signature using verify, but also it needs to make sure that the message that it's being signed is its own domain name. So bank.com might look at this and verify, yeah, okay, fine, it's like a good signature for bank.com. But when the real bank tries to verify, what it's going to call is verify kpub, the public key for the expected device, and it wants to verify the message challenge concatenated with bank.com, the real thing, and check if the signature is valid. And that'll say not okay, because indeed that's not what the signature is signing. It's signed a different message. So this is how U2F tries to avoid phishing attacks, is by getting the browser to distinguish sites for the security key. Make sense? So that's the main trick there. Basically, there's a bunch of other cool stuff they do, and a bunch of sort of weird stuff they do about these counters and attestation that ended up being not actually super important. I mean, this is, I guess, a research paper. They deployed this stuff, but now that it's much more widely used in practice, I think people have realized the counter stuff wasn't that great or important. Attestation, maybe not the greatest idea. But having the browser send the origin to the device, that was fantastic. And this sort of dynamic key generation that we didn't get to also turns out to be, seems like a good idea. But these are sort of the two main tricks that U2F really gets right, or two new ideas that seem to be good ideas here. All right, any quick questions? Last minute. All right, thanks very much. See you guys on Thursday.